Welcome to 3B's World Podcast. I'm Boni. In the field of modern medicine, few tools are as impressive or as intimidating as the magnetic resonance imaging scanner, or MRI. These machines house superconducting magnets cooled by liquid helium that generate fields ranging from 1.5 to 3 Teslas. To put that in perspective, a 3 Tesla magnet is approximately 60,000 times stronger than the magnetic field of the Earth. Given that a compass functions by aligning itself with the strongest ambient magnetic field, a logical question arises. Why doesn't every compass within a several block radius of a hospital point directly toward the radiology department? Today, we explore the principles of field decay and the sophisticated engineering that keeps these massive forces contained. The primary reason a compass remains unaffected by an MRI scanner involves the inverse square law as it applies to magnetism. While the magnetic field at the center of the scanner is incredibly intense, magnetic field strength diminishes exponentially with distance. In a clinical setting, we often discuss the 5 Gauss line. This is the perimeter around an MRI machine, where the magnetic field drops to 5 Gauss, the level at which it is considered safe for people with pacemakers or other medical implants. Because of the way magnetic flux lines behave, this drop-off happens remarkably fast. A magnet that can pull a heavy oxygen tank into its bore at a distance of 2 meters typically has a field strength no stronger than a common refrigerator magnet once you move 10 meters away. By the time you reach the hospital parking lot, the signal is indistinguishable from background noise. Beyond natural physics, we have to credit human engineering. MRI suites are not just standard rooms. They are masterpieces of magnetic shielding. If left unshielded, the fringe field of a 3 Tesla magnet could interfere with electronic equipment in adjacent rooms or even affect traffic in nearby streets. Engineers employ 2 primary methods of containment: passive and active shielding. Passive shielding involves lining the walls of the scanning room with many tons of steel or silicon iron. These materials have high magnetic permeability, meaning they act as a conduit for the magnetic field lines, soaking them up and redirecting them back toward the machine rather than allowing them to leak outward. Active shielding is even more sophisticated. Modern scanners include secondary sets of electromagnetic coils located outside the primary magnet. These coils carry current in the opposite direction, creating a counter field that effectively cancels out the primary magnetic field everywhere except inside the bore of the machine. This ensures the powerful force is concentrated precisely where the patient is positioned, while the rest of the hospital remains a magnet-free zone. Finally, we must consider the nature of the Earth's magnetic field versus a local point source. Although the Earth's field is technically weak, it is uniform and global. It is generated by the geodynamo, the movement of molten iron in the planet's outer core. Because this field is thousands of kilometers wide, it exerts a consistent torque on a compass needle across vast distances. In contrast, an MRI is a localized dipole. It may be powerful, but its reach is geographically insignificant. Unless you are standing within the immediate vicinity of the scanner, the needle of your compass will always prioritize the massive, steady pull of the planet over the artificial, contained field of a medical device. In summary, the reason your compass ignores the hospital is a combination of the rapid decay of magnetic force over distance and the rigorous shielding protocols required for medical safety. The Earth remains the ultimate navigator, despite our best efforts to create sun-level magnetism in our basements. Thank you for joining me on 3B's World Podcast. I'm Boni. If you found this breakdown of invisible forces interesting, please subscribe and share the episode. Until next time, stay inquisitive and keep your bearings.